is Luca Caruso and I'm M.Phil Candidate from the University of Malta. So today, compared to my previous colleagues, I'm going to be talking about passive design solution towards nearly zero energy buildings. And this particular project that was funded through the Maltese local agency for research funding, MCST. I'm going to describe the process behind to reach the preliminary test results. So, with regards to the literature review behind improving the thermal performance, steady state of masonry building blocks, and there are mainly three factors. The first is insulating the block, and we are going to, in this research, we were doing also, we are initiating the material characterization, and in particular, the most complex element to study is the polyurethane foam. Several plastic or polyurethane foams are undergoing different process in order to let the heat pass through it. So basically, we have conduction through the polymetic material and through the blowing agent and gases, the first two parts. Also radiation inside the pore surfaces, but also convection. So the main point of an insulated material is to keep the air still. So those pores has to be as close as possible to avoid convection currents. Then another aspect that is very important is the geometry optimization, but also the lightweight aggregates and reducing the density. Because thanks to several simulation, finite element methods, and also finite volume methods, the researcher has demonstrated that when you design the geometry of this block, for example, you usually imagine a building block with cavities that are rectangular, and it's either a rectangle or a square. So for La Carrière, the aspect ratio of these cavities are 23.3, and when I say aspect ratio, it's the ratio between the height and the width of those cavities. Then also LP added the vertical, basically used diagonal webs in order to further increase the thermal path through the block. And with regards to electroamics, that they start showing the importance of reducing the overall weight of the block. It also is difficult for for builders to carry out. It's usually 30 kilos, the most used one. And when we replace the aggregates, so we go from, let's say, 2,200 kilogram per meter cube up to, let's say, 1,000, for example, we make a huge improvement. And also we select the proper aggregates in order to reduce the thermal conductivity. For example, in this study from Brian Arben and others, they basically demonstrated that when you reduce the concrete resistivity, and when you increase the concrete resistivity, that is the opposite of the thermal conductivity, is basically demonstrating that insulation can, and you also incorporated the other strategies. Insulation can only improve the thermal performance of the block up to 60%. To be more precise, on top we can see blocks that are the traditional blocks, so that you just you do a little bit of optimization, or if you don't know it, you don't do it at the same time, and you just add insulation. So the insulation is giving you the highest contribution to improve the concrete resistivity and overall also the R value, the thermal resistance of the whole block. Then when those when those optimization occurs, for example, in those cavities, and then the contribution of the insulation it's lower because it's already improved. So the point of this literature review is to demonstrate that when you produce a building block that requires mass production, this mass production can be disrupted by the introduction of insulation. So you have to be sure that the insulation has to work. So that's the whole point. And also you balance also the geometry optimization, including the mix design, improving the mix design. So this we go into the comparison between the conventional concrete masonry unit and the double C block. The double C block, as you can see, there are basically two concrete leaves cutted and slotted into each other, and the insulation element is holding them all together and is acting as an adhesion barrier, and also both an acoustic and thermal element. We use three types of methodology. Two are made basically simulation, and one is a simulation, the second is a desk-based calculation, and the third one will be in situ measurement of the U value. When it comes to the ISO 6946, it gives us a methodology to do the calculation, the calculation of the U values, as architects usually do when they do energy performance certificates. And what it gives you is that you calculate two types of thermal resistance. The first one is through the parallel path method that gives you an overestimation of the R value, and as well as you have the isothermal plan method that gives you an underestimated part. So then the ISO tells you to mix the two, you average them, and the actual R value is somewhere in between the two. Of course, you also, the more complicated is the block in this case, or the wall, the higher are the uncertainties. So you have to calculate as well an R value. Another important aspect to consider, also to take into account the Maltese practices for building walls, is to include a fairly thicker layer of conventional mortar, concrete mortar. So these are the data we inputted. The good aspect, the interesting thing about ISO 6946 that gives you also the space, so you manually calculate, also allows you to do simulation and more advanced simulation like the one in FEM. So the two are comparable because the inputs we used are the same, essentially the same. So as you can see, in order to calculate R value, the R up and the R low, you have to, let's say, disassemble the block into parts, and you have to calculate each R value. Okay, and then you reconnect all together. And then you do the same for the isothermal layers. At the same time, as you can see, the double C block, how complicated it is compared to the previous one. And I will show you why it's so complicated. And at the same time, here you can see the finite element method simulation that basically use DXF file. So you just retrace the shape, and then you can input inside the software and also associate to each color the material properties you need. And we did it for both the double C block and the all core block. And I will show you the results later. With regards to the third methodology, so we compared desk-based finite element simulation and in situ measurement of the thermal conductance. Is basically we built 2 rooms at the University of Malta, and the difference between the 2 rooms are basically that the walls are made up in a different way. One is made up of hollow core blocks, those building blocks they always use, and the other one is made up of double C block. In this picture you'll see just the double C block. And as you can see, we over-insulated the roof and the ground slab just because we wanted to have more heat transmission through the wall. And basically here we placed, this is the north side, and we placed the heat flux sensor and the associated thermocouples, but also we measure the indoor air and relative humidity, as well as comparing to the local microclimate, so outdoor air and dry bulb temperature and relative humidity. These are some of the pictures taken on site when we were building them, and a few images of the sensors, the data logger, the thermocouples, and the hygrometer and the digital thermometer. So, we were comparing the 2 type of calculation you can do through the ISO 16946. Is basically saying that when you manually calculate such kind of geometry, you get more or less an exact result. So we got 2.01 watt per meter square Kelvin. It's the U value, and including also the effect of mortars. And the effect of mortars didn't increase much. This is the U value calculated without mortars, and this is the same almost because it's made up of concrete. A bit of complication came with the double C block instead. And in this case, it's important to mention that the relative error when doing manually calculating the U value was quite high, was beyond the limit allowed by ISO, that is 20%. Also, this block is sensitive to the effect of mortar, so you need not only because the mortar becomes a thermal bridge, especially if you use conventional mortars. And then the final U value was 0.81. When it comes to the detailed method that is now required in order to understand which should be the thermal conductivity of this block, this one was calculated including render and plaster. So in the end we obtained a weighted average between vertical and horizontal section of 0.71 watt per meter square Kelvin. This instead is the similar calculation made for the hollow core block, and the hollow core block is giving us, when it's simulated through FAM, is giving us 1.8. So we got the exact results, we assume the more precise result with double C block, that is 0.71, and if you remember, the hollow core block was 2 watts per meter square Kelvin, and through FAM analysis we got 1.8, so there is a slight difference. I'm about to conclude. The results of the 8 days campaign still ongoing, because we want to measure both cooling season and heating season, and it's basically telling us that when you use in situ measurement of the thermal conductance, you won't get the exact results like we do usually for hot boxes, because there are, due to outdoor effects, there are a lot of oscillation. So you have to keep on doing those measurements for quite a long time. And that can be also more than 1 week sometimes, especially when you have when you have elements with high thermal mass, and that's density. So for the traditional block, we demonstrated that most of the time the U value of this block is between 2 and 2.5. So it's quite close to the calculation and main calculation. When it comes to double C block, it's between 0.5 and 2, but most of the time it's between 1 and 1.5. This is not shown in this presentation, but because these are the results that we framed the 3rd of May when we submit the paper. But we discovered that because of the component, by just studying the thermal conductivity of the materials, we understood that it's because of the components that is not performing as we are expecting. Yes. So in conclusion is there is an untapped opportunity to use simulation, finite element simulation, to predict the behavior of those components, so that we can know in advance what to manufacture in order to get walls that are energy efficient. And in my opinion, unfortunately, even though we are working with a manufacturer, local manufacturer in Malta, they are still not fully understanding the powerful of having an approach like that, that even though it requires more tests, but at least you can make sure that when you go into production, you know exactly what you're selling, and you know that you're going to the right direction. Thanks.
Many thanks, Luca. The novel masonry unit looks at such great potential and very interesting characteristics. Are there any questions from the audience? Yes, please.
Yeah, thank you for the presentation. Did you look at the variation in the compressive strength of these double C blocks as compared to the normal blocks? Because if these blocks are to be used in load-bearing walls, then compressive strength is very important. So if there is increase or decrease, that's one question. Second thing is that from the cross sections that you showed, the 3D views of the two types of blocks, it seems that in the case of double C block, this hollowness ratio is reduced significantly if you compare it with the first one. So when you reduce the hollowness ratio, that in itself will undermine the thermal insulation, although you are putting a material. So did you consider these two aspects?
Yes. When it comes to the compression strength, this was not part of this paper because we wanted to focus on steady state heat transfer. But we tested to destruction, and we demonstrated that while the conventional hollow core blocks usually is considered as a compressive strength up to 7 megapascal, distribution curve of let's say 12 of those blocks is giving us more or less 6.5, 7 sometimes. So they are quite comparable, so we can consider them as load bearing. Also, you have to understand that both rooms, so this room was built with hollow core block, and that are 7 megapascal, and this is built with double C block. So we can consider it as a load bearing component, masonry component. When it comes to the cavities, yes, they might reduce the compressive strength, but first and foremost they have to be vertical. because you cannot put it horizontal. Sometimes some researchers has termed the direction of the holes, and of course it's weaker, the block. But the most important thing that's why it was important to mention the research from Brian Harman. The point is, when you infill the insulation and you already have those two strategies, meaning geometry optimization, even through simulation, and also when you reduce the thermal conductivity of the concrete, you are already giving doing a very good job. The thermal performance, of course, also increases, but not that much as, for example, those traditional blocks when you insulate, when you put foam in this case. So it's a matter of cost then, and how you improve your mass production, in our opinion.
Thanks so much. Thank you.